Hi everyone, I'm Professor McBain, and welcome back to Chem 100, and welcome to our third video in the series on radiation and global warming. This third video is going to be focusing on greenhouse gases such as carbon dioxide and water vapor, and how light interacts with those gases to result in the greenhouse effect. Hi everybody, and welcome to part 2 of our radiation and global warming lecture. Technically, we left off on this slide where I'm returning to a discussion of all of the wavelengths of light that reach the surface of the Earth, and so we're about to get into this spot here where we're going to discuss how water and carbon dioxide interact with IR light and our greenhouse gases and what that even means. But first we need to have a discussion about heat, okay, because that's the warming and the global warming, right? So we need to talk about heat and molecular motion, and really the big take home here is that heat and molecular motion are the same thing, okay? So if you consider the kinetic energy, Ke, of molecules, right? So we're looking at everything at a molecular level. So not like me as an object that can have kinetic energy, but more like the breath that is coming out of my lungs as I speak to you here. The kinetic energy of molecules, from physics, we learned that we can find the kinetic energy, we can calculate it by finding 1/2 multiplied by the mass of whatever the object is, multiplied by the velocity, which is a fancy word for speed, squared. All right, so 1/2 mv squared is equal to an object's kinetic energy, whether that object be a large object like you or I, or whether it be a small object like a single molecule of carbon dioxide from our breath. But here's the thing, is that that kinetic energy is actually measured as temperature as soon as we're talking about molecules, or anything smaller than a molecule, of course, like a proton, neutron, or electron. So that means basically that if an object's kinetic energy increases, or if a molecule's kinetic energy increases, then that corresponds to an increase in temperature as well, okay? And so it's not like a cause and effect thing. This is like a definition thing, kind of like if Devin McBain grows 1 year older, then of course her age is now going to be 1 year greater than what it used to be, right? It's more like a definition thing. It's not a cause and effect sort of thing, okay? Now, people often have a hard time visualizing this, so we're going to hop over to a simulation by Boulder, CU Boulder, a PhET simulation. And again, if you did the extra credit activity, then you'll have already become familiar with at least one of Boulder's PhET simulations. Okay, so we're going to look at this simulation, which is just about gases. Let's see what we can do here. Fantastic. I'm just going to supply some gas to this system. Hey, come on. Let's do more particles than that. Yeah. So here's some gases, and they're at 300 kelvins. Kelvin is just another temperature unit. We're not going to really learn what a Kelvin is because it doesn't really matter for us. Okay, all that matters is that 300 kelvins is a particular temperature, and it is roughly room temperature. It's roughly around 75 degrees Fahrenheit. Okay. Oh, excuse me, that's my cat. So check this out. If I cool down this sample of gas, wow, look at that. All of the molecules are moving much, much less. Because by definition, subjecting any substance to something that is colder than itself is going to result in colder temperatures, which results in less molecular motion. I can do the opposite as well. I can supply a lot of heat Maybe try to look away while I'm supplying this heat, and then look back when I tell you to. Okay, it's ready. So now we're at 934 kelvins. All right, so I believe that this is about like 500 degrees Celsius, which must be around, I don't know, 700 Fahrenheit. But it's really hot in here, and check it out. Now all of the gas molecules are moving much faster. Okay. We also need to talk about different ways that molecules can move. So obviously these gas molecules are doing what we call translational movement. So let's talk about the types of movement that a molecule can exhibit. So the first type of movement that people usually think of when they think of movement is what is called translational. Translational movement is basically that like point A to point B type of movement. And this is the type of movement that the gas molecules in the PhET simulation were exhibiting, okay? We also have rotational movement, and that's exactly like it sounds. Something stays in place, but then it just spins, or changing angles. And finally, we also have vibrational movement. Okay, vibrational movement is where the molecule is somehow expanding or changing bond angles and then returning back to original state. You're gonna laugh, but torquing is an example of vibrational movement, because all that's going on is a person's body is changing angles at one spot and then returning back to its original posture, okay? So we've got all of these different types of movement, okay, and they all count towards a molecule's kinetic energy, and so they all count towards a molecule's temperature, okay? All right, so this is going to be important when we switch over to our conversation about IR. So let's talk about IR vibrations, okay? So some IR radiation is absorbed by gases in the air specifically because molecules are always vibrating, okay? So I just explained that this is a thing that happens. But if we go over and take a look at the Wikipedia page on infrared spectroscopy, we have this very lovely demonstration of all of the different ways that molecules can vibrate, okay? And so this is important because if you have a molecule that absorbs infrared light, what it does with that light is that it uses it to perform a vibration. So let's make a little note of that. If a molecule absorbs infrared light, it uses it to perform a vibration. And not just any vibration. Let's get more particular about this, okay? So this is the infrared spectrum of water, okay? And so this infrared spectrum is technically a transmittance spectrum. It's not an absorbance spectrum. What's going on here at the top, hey, come on, get out of here. What's going on here at the top is that if you have 100% transmittance of light, then that means that that light was not absorbed at all by the molecule, okay? But if you have less than 100% transmittance, then that means that the molecule that you are passing that beam of IR light through, the molecule must have absorbed some of that light, okay? So anytime that you see these dips, it corresponds to the molecule having absorbed that light. And if we go back to our little note from page 10, again, if a molecule absorbs any IR light, that's because it's using that molecule to perform a vibration, okay? So on this infrared spectrum that we have here on, I guess, page 11 of our notes, this particular wavelength of IR light tried to pass through a sample of water, but the water snatched it up in order to carry out an oxygen-hydrogen stretch type of vibration, okay? Same thing happened down here closer to about, what would that be, like 10,000 nanometers of wavelength. But this is where the HOH bending happens. Okay, so this is where the oxygen pushes out from the hydrogens, and then it comes back, and it might kind of go back the opposite way like this. So you're getting that level of bending going on. Okay. And so why does it happen at particular frequencies? Why do we know this? So recall from our discussions on light that energy is proportional to the frequency of light that the frequency that the light is vibrating, basically, and that is proportional to the inverse of the wavelength of that light. But guess what? Vibrations are waves as well, okay? So even like sound waves, right? You know how when something makes a sound, we always kind of show it in cartoony sort of ways by going like this? It's because that's how vibrations of sound actually move through the atmosphere, okay? And so if they're a certain distance apart, then that corresponds to like one sound tone. But if they are closer together, then of course they have a higher frequency, and that corresponds to higher pitches, right? And so just like light, if sound has a higher frequency, that corresponds to a higher energy. You know this practically because anytime that there's a high-pitched tone that is played in your ear, usually those high-pitched tones hurt your ears. And that's because they actually have higher energy. And they can actually do enough damage to your eardrums to bust them. Suffice it to say that this is what I'm trying to get at here for the time being, is that light has frequencies and vibrations have frequencies as well. Okay, so now here is the big takeaway. Here's the punchline, if you will. Okay, so if light hits a molecule and that light has the same frequency as the molecule's vibration that it can perform, then the molecule absorbs it and uses that absorbed light energy in order to perform the vibration. Okay, I mentioned this on the previous page. I said just in general that if a molecule absorbs any IR light at all, it uses it to perform a vibration. But this is where it gets a little bit magical, is that the energy of light, the frequency of the light, has to match the frequency of the vibration that's being performed. Okay? So the frequency of the light and the frequency of the vibration have to match, okay? And when they do, this is called resonant frequency. Okay, so a molecule absorbs its resonant frequency of light and uses it to perform a vibration. Perform that vibration. That's what I would say. Okay, so this happens for water. More importantly, this also happens for carbon dioxide. Okay, let's hop over to a nice little animation of this happening for carbon dioxide. But otherwise, all of the notes that I have for what happens with water, all of that happens with carbon dioxide as well, okay? And actually you can see that the difference between the areas of no transmittance, or I'm sorry, the areas of 100% transmittance and the strongly absorbed sections, you can see that carbon dioxide actually does an even better job of absorbing its resonant frequencies of IR light to perform vibrations than water does. Notice that water only goes from 100% to like 93.25% transmittance at the most, whereas carbon dioxide will go from about 92% all the way down to 0% transmittance. So carbon dioxide absorbs IR light even more strongly, and therefore it probably is going to perform those resonant vibrations to a greater extent. So we talked about the fact that thermal energy is actually kinetic energy of molecules, and that is measured by its temperature. Okay, and so if those molecules are right next to each other, like here's one carbon dioxide, here's another carbon dioxide, here's another carbon dioxide. That would be the neighbor cat, not one of mine. But you can imagine that if one of these starts vibrating because it absorbed some IR light, well, check it out. It's going to probably bump into the others that are around it and then cause them to start vibrating as well. And then both of these guys are going to bump into that one and cause it to vibrate. So as soon as one molecule absorbs IR light, then as soon as it starts vibrating, it can transmit that same vibration energy to another molecule, okay? So let's make a note of that. If one molecule absorbs IR light and starts vibrating, then basically it can pass on that vibration to molecules that surround it. I'm going to put a star next to this because this is basically the idea of transferring heat. Okay? Heat is the amount of thermal energy that gets transferred when a cold object comes into contact with a hot object. Hey, why don't we rephrase some of that? So a cold object is one that does not move very much, comes into contact with a hot object that is a moving object. So heat can also be transferred by radiation without coming into thermal contact. Don't worry so much about that. How it really happens with greenhouse gases is this sort of thing. We have an initial input of IR light to at least one molecule, and then even if none of these other guys absorb a photon of IR light, they still get vibrational energy transferred to them just by coming into contact with the one that got it first and started vibrating, okay? So then the more and more that this happens, then of course, as heat is added to the system, as vibrations are added to the system, then of course, this is the definition of a rising temperature. So here's another summary of what I just said on page 13. I know that I tend to do this, okay? So light energy comes into the atmosphere, and even if it passes through the atmosphere, it gets absorbed by the surface, but then re-emitted as IR light back into the atmosphere, okay? And so then if there is more IR radiation that gets absorbed by the molecules in the atmosphere, then of course the molecules are going to all vibrate more. And then that's going to increase its temperature accordingly, okay? And so what we have to understand now at this point is that there's going to be a certain amount of energy that comes from the sun, really, at all times, okay? And that amount of radiated energy, let's just assume that this is pretty darn constant, at least as long as the same face of the Earth is facing the sun at all times, okay? So then we need to think about, okay, well, if this is constant, how can it be that there's something that's going to change to increase how much IR light comes in and changes the temperature, okay? So if you imagine just like one carbon dioxide molecule here, then if there's a constant amount of IR radiation that can reach that IR molecule, well, then it's going to increase the temperature, this guy's temperature. Here, let's have a slightly different shade of red. It's going to increase this guy's temperature a certain amount and at a certain rate, right? So there will be a certain amount of change in temperature over a certain period of time, just due to this single molecule absorbing IR light. But what if we had a bunch of these guys? So let's draw more carbon dioxides. Okay. So if every single one of them is absorbing all of the various rays of IR light that could be coming through or getting re-emitted by the surface of the Earth, then every single one of them is going to be contributing to changing the temperature of all of them over a certain period of time, okay? And so they're all going to be adding vibrations. And so the more vibrations that you add, then that's going to lead to more and more and more of an increase in temperature, okay? And so that's the issue with global warming, is that if you are increasing how many carbon dioxides are in the atmosphere, then you're going to be increasing the rate at which the same amount of IR light from the sun has an effect on the temperature of the atmosphere. That's the deal, okay? So why don't we make one more summary of that fact? If you increase how much carbon dioxide is in the atmosphere, then you increase the effect that the same amount of IR light has on increasing the temperature. Okay, so that's the mechanism. Okay, so if we relate things back to our week 7 topics about like scientific claims and criteria and for those claims and whatnot, this is basically the mechanism by which things happen. Actually, it's not the mechanism at all. This is kind of like the hypothesis or the theory. Okay, why don't we be generous right now and let's just call this the hypothesis. Okay, and everything that I explained about how there are resonant frequencies of IR light, that is the mechanism by which all of this happens. This is the mechanism by which we establish this hypothesis. Okay, so let's press forward and see what we have here now. Okay, so again, this is just the entire greenhouse effect explained there, but it's all predicated on this. If you increase how much concentration of carbon dioxide is in the atmosphere, then that increases, well, the temperature, because IR light has more things that it can get absorbed by. Okay. And so, of course, we have here at the bottom, more carbon dioxide in the air is going to lead to an increased energy absorption and a higher average temperature. Okay. So it's one thing to propose a hypothesis like that, right? And one thing to explain how it could happen from a pretty good mechanism. But of course, it's important to be able to make predictions and even retrodictions about that, okay? So what we're going to look at in our next video is the data that could possibly connect these growing concentrations of carbon dioxide to global average temperature. Find out more next time.